Hey there, Mr. Weaver here, and this is Topic 6, Lesson 5, Exponential Growth and Decay. After this lesson, you need to be able to use the formula for exponential growth or decay to calculate a total over time, and you need to be able to solve word problems involving exponential growth or decay. You'll know you're successful after this lesson if you can use the correct formula in context, either growth or decay, calculate a total after growing or decaying over time, and determine when a population reaches a certain value. For exponential growth and decay, they pretty much use the same formula. Here we have the formula for exponential growth. It is similar to the formula for a general exponential function. However, instead of b, we have that parenthesis of 1 plus r. And then instead of x, we use t. So first, because this is growth, it is going to have a plus sign in the middle. So when you're choosing which formula to use, if your total is going up, then you're going to choose the growth formula, which has the plus. In this formula, a stands for the same thing that it did before, where a is the initial value. So that's going to be your starting value in the context. R is going to be your rate or your percent that it tells you. You need to remember to write it as a decimal. So if it was 10%, you would write it as 0.10. T stands for your time, and f of t is your total. In some problems, it might ask you about the growth rate. The growth rate is the percentage that it's increasing by over time. So grow implies that it's increasing. So for example, if it said that it's increasing 6%, then the growth rate would be positive 0.06. Again, we write our percent as a decimal. This compares to growth factor, which is 1 plus the growth rate. So it's what's inside the parentheses there if you were to combine them together. So if we had an increase of 6%, 1 plus 0.06 would be 1.06. So 1.06 would be your growth factor, where 6% would be your growth rate. Exact opposite of exponential growth is exponential decay, and the only difference is instead of a plus in our formula, it is a minus. So when you see problems with decay where the population or total is going down over time, then use a subtraction sign. Just like the growth rate, we also have the decay rate, where it's the percent that the initial value is decreasing over time. So example, if it decreased 6%, it would be minus 0.06. And just like growth factor, we have a decay factor where it's 1 minus the decay rate. So 1 minus 0.06, our decay factor would be 0.94. Let's start by looking at a problem that involves exponential growth. The population of Hillville grows at an annual rate of 15%. If the current population is 5,000, what will the estimated population of Hillville be in 5 years? In the problem, it tells us that it's growing, which means we need to use our exponential growth formula, the one with the plus sign. Then we need to look for our other things. So A, our initial value, R is our rate, and T is our time. It said the population currently is 5,000. That would be your start value. It has a rate of 15%. That is our R value. And we want to know in 5 years. So that's our amount of time. Now we can just plug these into the formula. So A is 5,000. R is 0.15. Remember, we need to change it to a decimal. And T, the exponent there, is 5. We can type this in the calculator as it is, or we could simplify the parentheses even farther to make our growth factor. Either way, if we calculate this out, Our total should come out to be 10,056.7859 and so on. But since we're dealing with people and we're just estimating the population, we could round that up and say that in 5 years, the population will be about 10,057 people. Before I have you do your problems, let's look at an example of exponential decay where we don't know how much time, but we need to figure out when it reaches a certain point. A video is labeled as a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. In how many days total will the video stop being a fan favorite? So here it says that it's decreasing, which is an indication that we need our decay formula, where it has the subtraction. Again, A is our initial value, R is our rate, T is our time. It tells us that initially on the first day she had 8,192. So there's our A value. Our rate was 25%, but it's asking how many days. So we don't know the amount of time. It does tell us that the total needs to be at least 1,000. So if we plug in what we know, the total is 1,000, the start value is 8,192, and our rate is 25%, 0.25. We need to figure out when it's going to get to 1,000. We can simplify the parentheses to get a decay factor of 0.75. Now, we need to be able to solve for an exponent. And you do not know how to solve for an unknown exponent, and in fact, it is not something that you are going to learn how to do this year. So, to solve this problem, we're going to enlist the help of Desmos and figure out when our function reaches 1,000. Here in Desmos, I can type in my function, so f of x equals 8,192 times 1 minus 0.25. I'm not going to simplify that out. But we do need to remember, in Desmos, you need to use x. So I changed, instead of f of t, I made it f of x. We'll just know that x is the same as t. If we zoom out, so we can see where our line is, here we can see that it's going down over time. Remember, we started with 8,192. My units here are only at 50 and 100. I need to zoom out quite a bit. I need to figure out when it reaches 1,000. So I can see going down here, eventually it's going to pass 1,000. One trick to figure this out, if you type in the next line, we want to know when our total was equal to 1,000. It will put a line when it crosses. Then, if we zoom in on that line and where our function crosses it, you can click on the point. Thinking back to when we did systems of equations, that intersection is when those two things are equal. So at 7.311, it was equal to 1,000. Once we go past that, so 7.312, we're down to 999. So we calculated out that our time was 7.31 days. If we want to go for whole days, then 7 is not quite enough. So the next day would be 8 days. So it took 8 days for the population to pass below 1,000. Now it's your turn. Try both problems on your side and we will go through them. One of the problems involves calculating the total, and one of the problems involves figuring out how long it took before it got to that total. Read through each. We will go through both next. All right, let's check the first one. You should have figured out that the population will be 5,573 people. Here's the formula you should have used. Our initial value was 12,000. It's decreasing, so subtraction. 12% is 0.12, and 6 years, so the exponent should be 6. In the calculator, we might have actually got 5572.849 and so on, but rounding it up, we would get 5,573 people. For the second one, you should have figured out that it would take about 17 days. Your original equation is 100,000 is equal to 120 times 1 plus 0.5 to the t power. Again, if we go to check with Desmos, we would have typed in our original function and set it and figure out when it's equal to 100,000. At 100,000, got to zoom way out. There's my 10,000s. All right, there's my line for 100,000. Now that I found it, I am going to zoom back in to make sure I click on the correct point because the y-intercept is also right there. Zoom in until I find it, 16.587. So 16.587 would round up to 17 days. 16 days, he wouldn't have quite enough views. He'd be close. 17 days would be the first time he is over that total. In this lesson, we learned about exponential growth and exponential decay. Exponential growth describes a situation where a population continues to increase by a % over time. In our function, f of t equals a times 1 plus r to the t power, we have f of t, which is your total, a is your initial value, r is your rate or %, write it as a decimal, and t is the amount of time that it took. If you want to determine the total, then plug in each of the values and calculate it out. Exponential decay, on the other hand, is the exact opposite. It's describing situations where the population is decreasing by a certain % over time. The function for decay is pretty much the same as growth. The only difference is it's subtraction instead of adding. Certain situations we might want to figure out when the population or the total reaches a certain value. To do this, we need the help of Desmos. Make sure you use x instead of t, and then find where your function equals that value. The intersection point there is when they're the same, so you need to still determine if you want it before that total or after that total, depending on the context. After this lesson, do you now know how to use the correct formula in context for either growth or decay? Can you calculate the total after growing or decaying over time? And can you determine when a population reaches a certain value? If you're not sure about these things, go back and look at the 2 different examples and when to use each formula, along with how to calculate and determine when it reaches a certain point using Desmos. And that's the end of lesson 5 on exponential growth and exponential decay.